Protecting wires and cables in electrical circuits requires careful consideration of both overload and short-circuit conditions. The National Electrical Code and IEEE Standard 242.2001 provide guidelines for selecting and applying circuit breakers to ensure electrical safety. According to the National Electrical Code Article 210.8, branch circuits must be protected against overcurrent by circuit breakers or fuses rated at not more than the ampacity of the conductor. The IEEE Standard 242 states that conductors should be protected against overloads by circuit breakers or fuses rated for the maximum continuous load current of the circuit. These standards emphasize that the circuit breaker's ampacity rating should align with the conductor's ampacity to prevent overheating and potential fire hazards. For short-circuit protection, National Electrical Code Article 110.9 states that branch circuits must be protected against short circuits by circuit breakers or fuses rated for the maximum short-circuit current that can flow in the circuit. Similarly, IEEE Standard 242 says that conductors should be protected against short circuits by circuit breakers or fuses rated for the maximum short-circuit current that can flow in the circuit. These guidelines highlight the need for circuit breakers to handle the high fault currents that can occur during a short-circuit event, preventing damage to equipment and ensuring personnel safety. Selecting the appropriate circuit breaker involves several critical steps. Firstly, select a circuit breaker with an ampacity rating equal to or greater than the ampacity of the conductor it protects. This ensures that the circuit breaker can handle the normal operating current without tripping unnecessarily, while still providing protection against overloads. Secondly, choose a circuit breaker with an interrupting capacity rating that is equal to or greater than the maximum short-circuit current that can flow in the circuit. The interrupting capacity, or IC, is the circuit breaker's ability to safely interrupt a fault current without failing. If the short-circuit current exceeds the circuit breaker's IC rating, the circuit breaker may be damaged or fail to clear the fault, potentially leading to a hazardous situation. Thirdly, consider the time current characteristic of the circuit breaker to ensure proper coordination with other protective devices in the system. The time current characteristic, or TCC, describes how quickly a circuit breaker will trip under different overcurrent conditions. Proper coordination involves selecting circuit breakers with TCC that allow downstream devices to trip before upstream devices, minimizing the extent of the outage and preventing unnecessary tripping of the main circuit breaker. When conductors are used in parallel, special considerations apply. Firstly, if conductors are used in parallel, the circuit breaker must be rated for the total ampacity of all conductors. This ensures that the circuit breaker can handle the combined current carrying capacity of the parallel conductors. Secondly, ensure that the conductors are sized and connected properly to prevent overheating and overloading. Parallel conductors must be of the same material, size, and length to ensure equal current sharing. Unequal current sharing can lead to overloading of one or more conductors, potentially causing overheating and insulation damage. In addition to these specific guidelines, there are several other important factors to consider when selecting and installing circuit breakers. Firstly, use circuit breakers that are listed and approved by a recognized testing laboratory such as UL or ETL. These laboratories test circuit breakers to ensure that they meet applicable safety standards and performance requirements. Secondly, install circuit breakers in an accessible location for easy maintenance and operation. This allows for quick access to reset trip circuit breakers and perform routine inspections. Thirdly, regularly inspect and test circuit breakers to ensure proper operation. Testing can involve visual inspections, insulation resistance tests, and operational tests to verify that the circuit breaker trips correctly under overcurrent conditions. Finally, follow all applicable electrical codes and standards, including those established by local authorities. Local codes may have additional requirements or restrictions that must be followed to ensure compliance and safety. Understanding ampacity is crucial for proper circuit breaker selection. Ampacity refers to the maximum current in amps that a conductor can carry continuously under specific conditions of use without exceeding its temperature rating. The National Electrical Code provides tables, such as Table 310.15b16, that lists the ampacity of various conductors based on their size, insulation type, and installation method. These tables take into account factors such as ambient temperature, the number of conductors in a raceway or cable, and the presence of thermal insulation. When selecting a circuit breaker, it is essential to ensure that its ampacity rating does not exceed the conductor's ampacity. Overloading a conductor can lead to overheating, insulation damage, and potentially a fire. The National Electrical Code also provides guidelines for determining conductor ampacity under certain conditions. For example, if conductors are installed in an environment with a high ambient temperature, their ampacity must be derated to account for the increased heat. Similarly, if multiple current-carrying conductors are installed in a raceway or cable, their ampacity must be derated to account for the increased heat generated by the conductors. These derating factors are specified in National Electrical Code Table 310.15b3 and must be applied correctly to ensure that the conductors are not overloaded. Another important consideration is the circuit breaker's interrupting rating, often referred to as the interrupting capacity or IC. The interrupting rating is the maximum short circuit current in amps that the circuit breaker can safely interrupt without being damaged or failing. The interrupting rating must be equal to or greater than the available fault current at the point of installation. The available fault current is the maximum current that can flow during a short circuit condition. It depends on the source voltage, the impedance of the power system, and the distance from the source to the fault location. Electrical engineers typically perform short circuit studies to determine the available fault current at various points in the electrical system. These studies take into account the impedance of transformers, conductors, and other equipment in the system. The results of the short circuit study are used to select circuit breakers with adequate interrupting ratings. If a circuit breaker is installed in a location where the available fault current exceeds its interrupting rating, the circuit breaker may fail to interrupt the fault current safely. This can result in equipment damage, fire, and potentially injury to personnel. Therefore, it is essential to select circuit breakers with interrupting ratings that are appropriate for the specific application. The time current characteristic, or TCC, of a circuit breaker describes how quickly the circuit breaker will trip under different overcurrent conditions. The TCC is typically represented graphically, with current plotted on the horizontal axis and time plotted on the vertical axis. The TCC shows the amount of time it will take for the circuit breaker to trip at different levels of overcurrent. Circuit breakers are designed to trip faster at higher levels of overcurrent. This is because high levels of overcurrent can quickly damage equipment and pose a safety hazard. The TCC of a circuit breaker is determined by its internal design and construction. Different types of circuit breakers have different TCC. For example, inverse time circuit breakers have a TCC that is inversely proportional to the current. This means that they trip quickly at high levels of overcurrent and slowly at low levels of overcurrent. Instantaneous trip circuit breakers, on the other hand, trip almost instantaneously when the current exceeds a certain threshold. The TCC of a circuit breaker is an important consideration when coordinating circuit breakers in an electrical system. Coordination refers to the process of selecting circuit breakers with TCC that allow downstream devices to trip before upstream devices. This minimizes the extent of the outage and prevents unnecessary tripping of the main circuit breaker. To achieve proper coordination, the TCC of the circuit breakers must be carefully selected and coordinated. This typically involves using a time-current coordination study, which is a graphical analysis of the TCC of the circuit breakers in the system. The time-current coordination study shows how the circuit breakers will respond to different overcurrent conditions. The results of the study are used to adjust the settings of the circuit breakers to achieve proper coordination. In addition to these technical considerations, there are also several practical considerations when selecting and installing circuit breakers. Firstly, it is important to select circuit breakers that are appropriate for the specific application. For example, circuit breakers used in residential applications typically have different requirements than circuit breakers used in industrial applications. Secondly, it is important to install circuit breakers in an accessible location. This allows for easy maintenance and operation. Thirdly, It is important to label circuit breakers clearly. This helps to identify the circuits that the circuit breakers protect. Finally, it is important to inspect and test circuit breakers regularly. This helps to ensure that they are functioning properly and providing adequate protection. The National Electrical Code requires that circuit breakers be tested periodically to ensure that they are functioning properly. The frequency of testing depends on the type of circuit breaker and the application. Regular testing can help to identify circuit breakers that are not functioning properly and prevent potential safety hazards. In conclusion, protecting wires and cables from overload and short-circuit conditions requires careful consideration of both the National Electrical Code and IEEE Standard 242.2001. Proper circuit breaker selection and application are essential for ensuring electrical safety and preventing equipment damage. By following the guidelines outlined in these standards and considering the various technical and practical factors involved, electrical professionals can design and install electrical systems that are safe, reliable, and code compliant.